first of all, it's nice to be here. I see a lot of faces that I haven't seen for years. So, and my group is doing a lot of work in learning, reasoning, natural language understanding, and so on. And I'm going to give actually a new talk where I'm trying to convince you that it's time for reasoning, and I'm going to use time as a way to illustrate it. But let me start with an old example. For the people that read in the newspaper that we solved AI, this is a 68 thesis of Tenny Winograd at MIT, where he did Shrewd Law. It's a program that deals with blocks and basically interacts with human with respect to these blocks, trying to understand it to the extent that it can do something about it. And of course, Terry realized that a program like this will have to understand, execute, and interact, and this requires natural language understanding and reasoning, although he thought that he solved it at some level at least. Of course, this was very brittle. This was 68. We now work on a DARPA project that is called CWC, for Communication with Computer, that is doing the same thing. We haven't done it yet, so now we are playing with Minecraft. There is an architect that defines a shape, three-dimensional shape in this case, and tries to convey this message to a builder that interacts with the architect in order to understand and eventually build something. And you can look at this English here, and those of you that have tried to play with natural language understanding realize that we are far from doing it. So just to simplify it and give you a concrete example, we moved from this is Terry Winograd, to our build a giraffe example. And some of the teams that participate in this DARPA project even simplified the problem further. And they said, let's just assume that everything is on a table. We have blocks on a table. We're going to even avoid the reference problem, and we're going to name the blocks. So the blocks are named based on companies. You can see McDonald's, Toyota, UPS, Starbucks. And let's try to place blocks on this table relative to existing blocks. And this is a data collection that Jonathan Bisk did. And here is one example, real example, that he got from one of the crowdsources. Imagine that this is a chessboard. Place the UPS in H2 and McDonald's in G6. That's one of my analogy examples. So non-trivial. I think we don't know how to deal with it. We don't know how to write programs that understand and interact relative to this. So we have some work to do. Of course, we have made a lot of progress in natural language processing, mostly with respect to tasks for which we have a lot of training data, mostly extraction tasks. And today I want to give actually optimistic thoughts and challenges from the perspective of reasoning and specifically learning to reason. How should we think about learning in the context of doing reasoning? And let me start, given that I want to talk about language, by giving you a natural language processing example. Can you read this? If you can, say it. Thank you. Make my day. Excellent. So everyone gets it. I mean, some people get it in 10 seconds, some people will take half a minute or a minute, but it's quite amazing how quickly people do it. And to me, this is natural language understanding. This is something that you do all the time, every time, whenever you try to understand what I'm saying behind my fine accent, whenever you try to communicate with someone, what are you doing here? You identify a lot of units. Some of them are images, characters, and so on. You consider multiple representation, multiple interpretation. Each one of these units, standalone, has multiple interpretation. Maybe you have a distribution over different interpretations. But when I put it all together on one slide and you know that it means something, very quickly people are able to understand what it means, to identify one coherent explanation for all this, something that makes sense given the context, given the fact that I told you it's a puzzle and so on. And to me, this is really natural language understanding. So I think about natural language understanding as something that requires global decisions, that require a lot of local decisions driven by different models, trained different ways, different times, different scenarios, different conditions. It requires the ability to put these predictions together in a coherent way, and it requires knowledge that guides the decision so they satisfy expectation. And coherently and expectation are important words here because these are all knowledge-intensive components. So the thesis of this line of work is that natural language interpretation is an inference process that is best thought of as a knowledge constraint optimization problem done on top of multiple statistically learned models. Now, if we talk about inference or reasoning, just going a little bit back to history, we used to think about symbolic reasoning in AI. Nowadays, the new generation thinks that symbols is an evil invention of old AI people. Not the case. Really, language is a symbolic system. So this table is really a collection of things in the world. So you can think about communication and all of the modes that we use, speech, gestures, writing. These are continuous signals, but symbols are really the invariants of this communication, and they are very important. And of course, much smarter people like Yuval Harari wrote about the importance of symbols in language. My favorite philosopher, Sol Kripke, talked about naming things as the key to communication and cognition. And I think we shouldn't forget that when we try to move forward in this area. So perhaps one of the thoughts that you had when I talked about symbols was this guy, Aristotle, that was actually the first one that talked about formal logic, syllogism, and so on, known for this, for example, for this famous example. But I actually want to ask another question about it. Did Aristotle have a laptop?
No.
Most of you think that no, and most of you laugh because it's a funny question. Even though if you Google for it, you'll see that the answer is yes, because there is a book that is called Aristotle's Laptop. But clearly the answer is no, and the question is, how do we do it? So today's NLP really addresses well-defined tasks for which we have a lot of training data. But who asks the questions? So in this case, maybe you develop a strategy in a second or less that is composed of something like this. Approximately, when did Aristotle die? We don't need to know exactly. When was the laptop invented? And then which of these events happened first? How do we do it? I mean, how do we come up with these strategies? So I think the question isn't whether we need reasoning, but rather how to do it. How to determine strategies like this on the fly. And also how to train for it. What kind of learning do we need to do to supervise this sparse event? I assume that you've never seen this question before, and I assume that each one of you can ask on the spot 17 other questions like this. So I talk mostly about this supervision in another talk that I call incidental supervision. Today I'm going to focus on some interaction between learning and reasoning, because AI thought about reasoning a lot. I mean, traditionally, AI thought about reasoning as an area that was completely separate from learning. In 94, 95, 25 years ago, together with Ronnie Chardon, we wrote a sequence of papers. This was actually part of my PhD thesis that was proposed in reaction to the fact that AI kind of completely decoupled learning from reasoning, and we suggested a theory that was called learning to reason. I'm not going to bore you with the details. This was really a theoretical framework, but the key idea was that we argued and proved under some assumptions that reasoning should be studied together with learning and the representation it produced. So today, this is called end-to-end, but more seriously, what we left open, and I think is an important question that all of us should think about, is to understand when to decompose learning from reasoning, when to decouple learning from reasoning, And really, this is a question that is at the heart of compositionality, reasoning, and so on. And I think there's no better domain to think about this than natural language or natural language understanding. So let me jump right in to some formulation that I'm going to play with as we go. This is just a simple linear objective. We called it constraint conditional model. It's a model that allows us to think about a wide range of reasoning tasks in natural language understanding. You can think about it, if you know about it, as abductive reasoning. Basically, it's a reasoning for the best explanation or the best assignment to a group of variables. What we have here is a linear function where you have a collection of phi x, y. X is the input, y is a set of variables that you want to assign values to. A lot of problems can be formulated this way. And you can think about these as features, models, neural networks. Non-linearity comes here, and you can do whatever you want with it. And then you have a weight vector, a linear function over these models. And this is, again, a very, very expressive, even though people forgot about it. Any logical function can be modeled this way. And then you have a component of knowledge. Think about it as constraints or soft constraints, along with a weight that is the penalty for violating the constraints. And this C of xy models how far is an assignment y from a legal or expected assignment. So you can think about it this way as an objective function that is convex. You can differentiate if you want, or you can think about it as an integer linear program if you want. And sometimes, for modeling perspectives, it's actually very useful to think about it as an ILP. One advantage or one observation that you want to make here is that the variables themselves are models. So it gives rise for recursion if you want to do it. But the most important thing here is that it opens up a lot of questions that we want to be able to address in this context. What are the variables? How to represent the knowledge? And of course, the question of whether this is expressive enough. And I would argue that in many, many contexts, it is expressive enough because all Boolean functions can be represented as sets of linear constraints. And any map problem, maxima posteriori problems with respect to any probabilistic model can be formulated as an ILP. In terms of the computational processes, it brings up questions of training. What do we want to train here? Do we want to train the W and the U together? Do we want to train them together? Do we want to train the intermediate function phi of xy? Or do we want to bring them from home because we train them in other contexts in different situations? Do we want to train jointly? Do we want to decouple things? There has been some work, some theoretical work that tries to understand and answer some of these questions. But clearly there's a lot of questions here on the way to reasoning, which I'm defining here, or hand-wavingly defining as a function over learned models, and really as a way to push this function over learned model to satisfy or minimally violate output expectations. So I think we know today that there are things that we cannot do directly with this. We have to extend it a little bit. But it has been used extensively and successfully in many, many natural language understanding tasks, and still is a good framework to think about further progress in language understanding. So with this Aristotle in mind, or this question about Aristotle in mind, I want to devote the rest of the talk to thinking about reasoning in the context of time. So this was a question about time. And I want to talk about a few temporally related or temporal reasoning related tasks, temporal ordering of events, along with learning and inference paradigms that support reasoning with respect to it, the acquisition of temporal common sense, and some supervision paradigms that come up when we think about it. So again, this is far from exhaustive. I'm going to give at the end many other examples, or a few other examples, where this type of topics that I'm bringing up here can help us with. But from the NLP perspective, it reflects an important move from natural language understanding of a single sentence to understanding of a situation. We want to talk about events. And from the learning and reasoning perspective, it highlights important issue relative to supervision, combining learning and reasoning, and so on. if I'll have time, I'm hoping to give at least a short video or some of the slides on information pollution, which is another natural language understanding inference task, which hopefully will at some point have some societal impact. So let me start talking about temporal relations. So here is a piece of text, and I highlighted a few events there. The goal of this task is to identify the events and think about the relative order of the events. So think about generating this graph where edges could be relations like before, overlapping, included, after, and so on. A very difficult task. In fact, it's difficult even for human beings, because if you have n events in a paragraph, you have to deal with n square edges. Not easy to do, but we have strong expectations from the output.
Nobody was hurt. What does it even mean? It didn't happen before or after.
Say it again?
Nobody was hurt, and you have a node saying hurt.
Okay, good question. Keep this question. Okay. So I'm going to say something about it, but I think it's an excellent point that was actually omitted for most of the literature on this, but I'm going to come back to it. But let's assume that all the events are comparable, and I can add edges between them. So we know that they have to satisfy transitivity. If A is before B, B is before C, then A is before C. And we also have some weak constraints, because some events tend to precede other or follow others. So if you sit on an event, you have some distribution of what might happen next.
Following up on Daphne's question, non-events do not fit so nicely into this framework.
So in this case, I'm talking just about events.
No, but no one was hurt. It's a non-event.
Yes. So, and there could be other types of semi-events, and I'm going to get to it. Yeah.
Things like the weather was nice that day.
I will not call this event at all, but hurt at least passes the first filter, because it's a verb that typically represents an action. So the importance of this task hopefully is clear. I mean, I can think about these two events. But by the way, typically events come with arguments, and I'm kind of omitting this level of granularity here. But in this case, I don't. And you can think about people were angry before police used tear gas. Or you can think about the other way around. Police used tear gas, and therefore people were angry. And basically, you want to be able to use the context as a way to distinguish between these two possibilities. So it's completely clear that the context and other events in the context are essential in order for us to make decisions. So, for example, perhaps we know something about the relation between reaping and monitor, and this could help, or cascaded and reaping, and this could help us to determine other relations between them. So overall, the question for us is how to label this graph. The task is very difficult. So as of 2015, for example, these were the state-of-the-art results. About low 50s, even if you're given gold events, which indicates the difficulty of this task. So the first observation to make here is that temporal graphs are structured. For example, just if you take transitivity into account, you know the temporal relations are not independent. If you know that cascaded is before ordered and cascaded overlaps with reaping, reaping must also be before. Yes?
Doesn't the text usually assume like some kind of linear ordering in most cases? So I would be surprised if the baseline is so low.
The baseline is very low, partly because of very difficulties in annotation, and partly because the order in the text is not necessarily the temporal order. I'm going to give some examples of that. So the first thing that is clear that we want to do here is global inference. We don't want just to identify each edge in isolation, but rather we want to be able to enforce some results. So if you have these three edges here, and you just go for and let's assume that these numbers, they represent a distribution output for my classifier, my model, for which is the relation between them. Let's say I have just two relations. I don't want just to take the mode, because I can end up with a graph like this that makes no sense. So I want to be able to look at all the combinations, at least conceptually, score them, and choose the highest scoring combination that does not violate our constraints. And you can formulate this as an ILP, exactly the same formulation that I showed before, and get better results. So here is an example of an ILP that will model this problem. So we are maximizing the score of the entire graph while enforcing some constraints. What you have here is a Boolean variable that represents what is the relation, let's say in this case just before and after. And you have a coefficient, a real variable that represents the score coming from a model. And you want to do this subject to some uniqueness constraints. Every edge can take only one value, and transitivity constraints. The question now is, how do we learn? So how do we learn these models I of ij? And hopefully the examples that I've shown before illustrates that local learning is not sufficient. If all you know is ripping and ordered, the decision is difficult even for human, because you really need to know that cascaded is in the context and the value of the relation between cascaded and ripping, cascaded and ordered, in order to be able to determine the order between ripping and ordered. Otherwise, you'll train a model based on the gold, and it will overfit because it doesn't really have information in the context to accept this, to know the specific order. So we have to do some joint training here, and there's an area in machine learning, structured learning, that basically is doing just that. I mean, I could have given this talk 10 years ago. I'm not going to give details on structured learning. I assume that most people know what I'm talking about. I want to attend to another phenomenon here. Once we agree that we want to do structured learning, let's look at this. If this is the input that I give my model, more than 10 people have event 1, police said, a car event 2 on Friday in the group of men, and I'm going to ask you which event happened first. It's going to be hard. All I gave you is the context, but it's not sufficient. I can add this information, and now you know. So really the lexical information itself is very important here, because you need priors. And the question here is, how do you get these priors, this common sense temporal information? And this is one of the additional steps that we've done here. And this perhaps will answer some of your questions. Here is one example. So we built a system that acquires common sense, probabilistic common sense among events, ran over many years of New York Times with a basic system that was developed based on the two steps that I've done until slide 27. What you can see is that sometimes the order of the text, for example, ask appears before help, and indeed 86% of the times ask happens temporally before help. But accept and propose, only 10%, if the order in the text is accept and then propose, only 10% of the times accept actually appears temporally before propose. And you can develop this for many, many relations. Here are some examples where, given an event like a bomb, I have a distribution of what has happened before it and what could have happened after it. You can look at investigate here, and you can see that something makes sense. Kill will happen before, steal will happen before. For the people that write too many grants, after grant, you will see use, pay, and work. And before grant, you see write, request, seek, and so on. Makes sense. So with this knowledge base, and of course, this is not the only common sense, temporal common sense that you want to be able to use, but this is one of them that contributes a lot to understanding order between relations. Here are some other examples of temporal common sense. So what you see here are distribution over typical time of things, breakfast, brunch, lunch, dinner, or typical duration of things, like drive, nap, flight. So there's a lot of other temporal common sense that people have and use it when they do temporal reasoning, and we want to be able to acquire them. I'm not going to use these type of things in the context of the talk, but I am using these kind of things in the result that I'll show later. So how should I use it? You can make these probability distributions. And then at inference time, basically what you do is you add to the objective this as a regularization term, the same objective that I showed before, and you can get a way to incorporate this type of knowledge in a soft way into your decision. Okay, so far I talked about these things, and I want to talk a little bit about supervision. So I already indicate, before I get to supervision, a system that puts everything together. I have to use some deep learning in this talk, otherwise I won't get paid. So we actually put all these components together into a neural architecture that helps a little bit over other architectures. So we have a system that composed of LSTM that basically takes as input word embeddings and identifies hidden vectors, events. We have a feed-forward neural networks that takes this and predicts the label of the temporal relation, and this is followed up by an ILP formulation to correct the output and guarantees that we only minimally violate the constraints, plus a CME's vector network that allows us to support generalization over the temporal relation, the prior knowledge that we've discussed before, because the prior knowledge actually is discrete. For specific events that we've seen enough time, we have information, but for sparser events, we need to be able to generalize, and this component helps with that. Okay, so here is what happened over the last 4 years in temporal reasoning in NLP. So we started with the state of the art was around 50, and with basically the steps that I described before, we moved today to around 80% F1, or close to 80% F1. And this is, several things, including structured learning, common sense information, better representations, and so on. There's one step that I skipped because it didn't fit nicely with the supervision idea, but I want to mention it, and this is the question that Afna asked earlier. So the improvements really involve another conceptually important step, and that is the fact that not all events are comparable. So before, people were looking at events and looking at the complete graph and try to annotate it, but events really, the way we think about it, reside on multiple axes. Some of them are real events, some of them are intentions or thoughts or hypotheses, and so on. So we define, I think, something like 6 axes, and you should be able to compare events along a given axis, but you cannot compare events across axes. This turns out to simplify the annotation task very significantly. Inter-annotator agreement jumped by about 20%. It's much easier for humans to do it. We have a little bit less data, but we have much, much higher quality data. And with this comes significant improvement in the temporal relation identification. Okay, so, and as I said, I want to get to supervision. So what kind of supervision signals can we get when we play this game, and why? So let's go again. Okay, so first of all, in principle, so what we are doing here, and in many, many other problems in natural language understanding, is we're trying to induce semantic representations and make decisions that depend, and making this kind of decision requires supervision. There's no question about it. The question is what kind of supervision and how do we get it? So the standard machine learning methodology today is this boring 3-bullet protocol. Define a task, collect data for the task, annotate it, learn a model. And we can train better models today than we could 10 years ago, but we actually haven't changed the methodology. And I think that we will never have enough annotated data to train all the models for all the tasks that we need this way. In fact, I think that we don't even know what are all the tasks. Most of what we learn, we don't learn by training on a lot of examples. We actually use signals from multiple, that we collect in multiple scenarios indirectly. The current protocol is really not scalable, sometimes impossible, and often makes no sense. And most of the decisions that we really care about are too sparse so that we cannot directly train for them. So I'm not saying it's not okay to use supervised learning. In many cases, it's okay. In many cases, definitely if you want to build an application for something, that's often the right methodology. But in most interesting cases, learning should be driven by incidental supervision. Thinking about temporal relations, as I'm doing today, provides a way to think about one aspect of incidental supervision signals, and I'm going to go to it. So here is a paragraph that you've already seen, and this is a potential graph that you want to be able to annotate. And now, by the way, another answer to your question was that I didn't give you all the label. One of the label is vague. So even before before we made the recognition that not everything is comparable, people who annotated as one of the label vague where it wasn't clear what's the right thing to do. So there are 6 or 7 labels for this task. I just don't mention all of them. But what is clear is that I have to touch and square edges. And what you typically get from annotator is something very, very partial because it's too hard for them. So the question for us is, what level of supervision is really needed? And of course, there's also the algorithmic approach that I will not touch on today, how to gain from this. I'm just going to address the question of, do we really need exhaustive annotation? So the intuition is that if the structure is tight, that is, if there's a lot of constraints, and knowing some of the edges is sufficient or constraining enough, I don't need to annotate all the variables. A partial set of signals can supervise all. So the way to quantify it, we're going to play the following game. We're going to assume that we have a budget of annotation. On the left side, the blue one, I'm going to use the budget to annotate complete graphs, but a smaller number of graphs. And on the right side, the red one, I'm going to annotate more graphs, but each one of them I'm going to annotate partly. The result is actually this beautiful graph on the right that shows that with the same budget, partial annotation actually beats complete annotation quite significantly for this problem. The way to think about it, I'm going to introduce some notation. This is a structure for me. It's a collection of D, Y variables. Now, of course, not all the assignments are feasible because of the constraints, so I'm going to call it C of LD. I'm introducing this notation of Fk, which is the size of the feasible subset after I've given you K labels. And using this, and this is an example, so there are 4 nodes. I gave you 4 labels, and now I'm left with only 2 possibilities. And with this, I'm defining the benefit of K label, which is this Ik, how much of the feasible set has been disqualified by K labels. Of course, I want that this function will grow as fast as possible as a function of K. And this is, again, the same intuition that I've expressed before. And indeed, what you can see is that this Ik, the benefit of K labels is concave. And for example, in this problem, it goes up quite nicely. And the difference, Ik minus 1, the benefit of a new label is shown to be diminishing. And you can see this for multiple problems. You can see on the top left, Ik minus 1, how fast this goes down as a function of the graph structure. For chain, which is this temporal relation extraction, it goes down fast, and you can see this nice performance graph. For other problems, it doesn't contribute that much. For others, it contributes even more. And all these graphs were generated using a constraint EM algorithm, a Codel algorithm that we've been playing with for a few years now. So just to add a little bit more understanding for what is this IK, without giving you the exact definitions, IK is really the mutual information between Y, the set of assignments, and AK, which is the set of partial labeling, or random variable that provides partial labeling, where both Y and AK follow the uniform distribution. This is a slight problem with this framework, because of course I don't want this to follow the uniform distribution. Some edges are much easier to annotate than others, but currently the theory that we have works under the uniform distribution. The important thing is that this provides a view on structured annotation. Any signal that has non-zero mutual information with Y can be viewed as an annotation, and it points out a way to understand and quantify the value of indirect supervision signals. Not only the partial supervision that I showed here, but more generally, weak signals can be treated from this perspective. Okay, so we cannot answer this question yet. We don't know whether Aristotle had a laptop or not. We don't know how to answer this question, but we're trying to make progress. There are a few other tasks that hopefully are filling the gap between where we are today and answering these kind of questions. One of them is this challenge set for temporal reasoning problems, along with a baseline approach. I can give a couple of examples. So we deal with typical times, we deal with event frequencies, we deal with event ordering, and we're trying to make steps toward this. Now, this is not the only problem that can be dealt with these kind of techniques. Here is another example from question answering. Whenever we have sparse question answering challenges, that is, the answer isn't just extracted as a span of text, and you can train over 100,000 similar looking QA, you have to be able to generate representation and then do some reasoning over the representations. The same type of reasoning that I've shown today in a simple example of temporal reasoning. Over there, we're going to have a few more constraints, some structural and some more semantics. You can also think about another component for this in this puzzle, which is how to decompose the questions. I mean, I talked about it when I presented the Aristotle problem. Here is a simpler question, but again, like who kicked the longest field goal in the second quarter? I want to be able to decompose the question to executable components so that I'll be able to go to text or maybe some background knowledge, address each one of them, and then put them together in something that you can think about as some kind of a semantic parser. So all these are components of this framework that eventually, hopefully, will allow us to answer the question of whether Aristotle had laptop and a few other questions that we are dealing with in this case. So this ends the first or the main part of my talk. I want to spend a few minutes talking about something else. I try to give you a sample from a research program that attempts to address what I think are some of the key scientific and engineering challenges between us and understanding natural language. I talked a little bit about reasoning, with hopefully bringing up to your mind the question of to decouple it from learning or not to decouple it from learning. And the question of supervision. How do we think about learning when we actually want to do reasoning? And I did this in the context of temporal reasoning tasks. So I actually want to skip to something else. And I think I have about 10 minutes. Okay, so this line of work is about information pollution. So information technology started with a lot of optimism. We hope that it is going to make significant impact on education, medical care, science, public policies. What happened at the end is information pollution that actually bothers us everywhere and all the time. This is my definition following Levent-Orman of what is information pollution, the contamination of the information supply with irrelevant, redundant, unsolicited, incorrect, and otherwise low-level information. Now, this hasn't started today, hasn't started with Trump, nor with the analogous members here. It's really something that happens all the time. I think that the key.
Can I ask a question? So we know for ages that one man's noise is the other man's signal in the sense that what you call pollution depends on what you try to do.
Yes.
So it's not an absolute term.
It's just. I don't want to argue about the terminology, but basically, if you see the goal that I'm presenting here, I think it will be a little bit clearer. So I'm referring to the fact that there is way too much stuff out there, and therefore it's very easy to not know what's out there at all.
Of course, there's a lot of irrelevant information, but what's relevant depends on the task.
Yes. So let me say a few more things, and then let's see if at least my first step toward this solution is something that addresses this or not. So, but basically, I'm trying to say that factual information or lack of is not really the core of the problem. I think the core is different. The core is that there's a lot of things that people want to know. Most of the interesting claims that people are making are not black and white, but rather has multiple perspectives. In order to make progress in this, we should be able to move forward in multiple steps. Understanding the sources is a very important step here. I'm not going to talk about it here. There's a paper in ACL that addresses our work on understanding sources. Understanding the evidence is, I'm going to say something about it here. And this is the perspective that we are taking on it. We call it thinking about perspectives. And the idea is that we want to be able to take claims that appear in the news media or literature, or as far as I'm concerned, when you search the web for what to do if I have a pain in my neck, and think about and identify multiple perspectives relative to this claim. Each perspective will come with a piece of evidence that supports it. And this way, it will allow us to provide the information that is out there already in a more organized way and allow people to be, hopefully, more open-minded, less afraid, more likely to consider other views. I'm going to show, rather than talk more about it in any technical way, I'm going to actually show a short video. It's going to be 3.5 minutes that comes from a demo that we developed for this system, and I think we'll do a better job of explaining how we think about it. Okay.
One key consequence of the information revolution is the significant increase in contamination of our information supply. Over time, this has resulted in radicalizing effects in our societies. Many entry points to information, such as search engines or social media, are over-personalized to reflect our existing beliefs. As a result, many of us are trapped in bubbles of like-minded groups. We only interact with and hear those who we tend to like. This is especially true with respect to many discussion-worthy topics, where there might be multiple valid aspects to the problems, and all of these views could be reasonable under different worldviews. In this work, we present Perspectroscope, a web-based system which lets users query a discussion-worthy natural language claim, and it visualizes different arguments with respect to the input. The system lets users explore various perspectives that could touch upon an aspect of the topic at hand. Suppose you are curious about various aspects of using animals in lab tests. So, you issue a claim to the system. Animal testing for medical research should be allowed. The system comes back with a range of perspectives, each with a stance relative to this claim. On one hand, there are various arguments that oppose the claim. For instance, by citing the cruelty of such tests and the suffering that they incur on animals. And even further, such tests on animals don't necessarily guarantee good results on humans. On the other hand, there are also arguments in support of this query. Using animals as test environments could be a necessity for developing certain medications. Such tests sometimes can save human lives. Each of these perspectives are opinions possibly in support of the given claim or against it, and thus they constitute a particular attitude towards a given claim. More broadly, by viewing the world as perspectives, the goal is to give the users the understanding that each story is not black and white, but really it has more than one perspective. And by going towards such representation of the ideas, we want to help individuals become more open-minded about learning views that they don't necessarily agree with. Let's take a different example. Social media, like Facebook or Twitter, have had very positive effects on our lifestyle. Again, there is no single way to respond to this query, but rather there are many responses that form a range of perspectives, each with a stance relative to this claim. To support this input claim, one could refer to the observation that interactions between individuals have become easier through the social media. On the contrary, one could oppose the given claim by pointing out their negative impacts on productivity or the increase in cyberbullying. Our system is built via a combination of retrieval engines and learned classifiers to create a good balance between speed and quality. Retrieval engines are used to quickly select candidates for perspectives and evidence documents. These documents are retrieved from a pre-compiled pool of documents as well as Wikipedia content. And the learned classifiers make the final fine-grained decision-making on the given set of candidates. Additionally, our system is designed with the mindset to get feedback from users of the system. The user could give us feedback about whether a perspective is relevant or not, whether a stance is correct or not, etc. It's important to note that we have not completely solved the problem. For instance, our system could make mistakes on retrieving relevant perspectives. And all of these happen because, of course, natural language is extremely complex with various exceptions, which makes it difficult for machines. Beyond this, there are algorithmic components that we have not addressed here and are opportunities for future work. For instance, the system provided here does not provide any guarantees in terms of the exhaustiveness of the perspectives in the world. We hope that some of these challenges and limitations will be addressed in future work.
Okay, so as I said, there's a lot of this is really an initial step in this direction.
What was the highlight of today?
There's a lot of work to do in this direction, but hopefully to your questions, this is what we're trying to do. There is really, what we're trying to do here is to position it from the perspective of natural language understanding. What are the tasks that we have to solve in order to be able to support this kind of direction? The classifier that were mentioned, there are really textual entailment classifiers. There are several textual entailment tasks that you can define there. Dealing with trustworthiness is something that doesn't exist in this system, but something that we started to look at basically by following sources and algorithmically trying to understand.
Task is the IBM debater or not?
I don't think so. So there are relations clearly to the IBM debater, but we are not debating. We are basically presenting information as a function of processing what's out there. And what we've done so far is basically developing a data set that allows people to ask these questions, train models, and maybe if they want, change the way we ask the question and do it better. So I think there's a lot of questions in this area. All of them have to do, from my perspective, with better natural language understanding, or many of them at least, not all, have to do with better natural language understanding. Basically, I think a new challenge, an important one to the community. So let me stop here. Thank you.
Questions?
Yes.
How do you measure success?
Here?
Yeah.
Okay, it's a good, excellent question. So, so I'll tell you something that we've done a few years ago when we kind of started. We took, and we were now trying to do it at a much larger scale. We took groups of students. We presented questions that we think have perspectives, like a question, is milk good for you? We interviewed them, we tested them basically with respect to various perspectives on this topic before the tests. We then gave them, half of them, the standard kind of Google interface and our interface, and we tested them at the end trying to see whether people tend more to look at other views if we give them our interface. Our interface in this experiment was a little bit more enriched. In addition to perspectives and evidence, we also gave them, next to every piece of evidence, level of expertise and level of trustworthiness of the experts that have written this evidence. And what we've seen was actually quite optimistic. We saw that people that use our interface tend more to look at top experts on the other sides that were different than their original view. So that's how we evaluated it. If you have better ideas, I'm happy to take them. But I wanted to see whether it actually makes a difference, whether people tend to kind of a little bit even look outside their bubble when you present the information in a better way.
So your metric was part of the bubble. It was the specific, that specific aspect.
Yes, yes.
As you went into the last part, comparing it with the IBM debate, which has a different purpose but does some of the same thing.
Okay, so I agree with you. So there are two levels. One is the success of this whole kind of way of presenting information, and there's also the question of the technical, question. How good are we in finding perspective and finding supporting evidence and so on? And that we are doing the standard NLP way. We annotate the data, we got crowdsources to help us, and we measure the quality of our programs against gold standard. We have not measured against the debater. I think maybe in some cases there could be some overlap.
So the first part of your talk, you talk about temporal. And this is really a special case of a much more general membership queries about whether something can happen outside of this set or inside of this set, which is actually easier to formulate than temporal relationships. And it brings us back to machine learning, I think, in a much clearer way. I mean, can Aristo and laptop live together? This is not necessarily a temporal question. The question is, do they belong to the same type of set in some sense? Where, time errors is just one way of doing it.
Yeah, I'm not saying that this is the only way to view it. I think there are many issues that we have to address. Spatial issues, temporal issues.
Space or time, or space and time.
And I started with an example from spatial reasoning. We have to be able to address all these. I just used the temporal example, which is one of the projects that we are working on, as an illustration for where I think we need to go beyond the standard machine learning methodology, because...
You convinced me that it's really beyond the standard machine learning.
How do I answer this Aristotle question otherwise?
Well, essentially, so each one of those terms, Aristo and laptop, will actually have a long list of knowledge about them. One of them is the time of invention or time of existence, but there are many others.
But I need to know that this is what I need to do.
No, so we learn those associations in the same way we learned associations a long time ago, and just by learning statistical connections between objects and symbols, which I believe you all do one way or another. But I didn't see anything that really gets out of machine learning by this particular graphical structure.
So I think that machine learning is clearly a component here. But it's not the standard machine learning that we are doing today. So my argument is basically that there's a lot of tasks, a lot of questions that I want to be able to answer that I cannot directly train for. It's an important day. Of course, the components here are going to be learning driven. There's no question. But what components exactly, how to put them together, how to decide on the fly, there's so many things that I know about, maybe Aristo and maybe about laptops and maybe about time, and I need to figure out what is my strategy for solution, and I have to do it on the fly. And I think that it's not the identify the task, train data, train on annotated data, and get a label. So, of course, inside there's going to be learning components.
It's a longer discussion.
Yeah. Other questions?
Okay, thank you.
Thank you.